Now, I want us to look at probability distributions. We've explained what a random variable is. Now we're going and diving into what is known as probability distributions. Now, what is a probability distribution by definition? I want you to recall some of the distributions which we talked about in descriptive statistics. There's a distribution which we talked about, which is the frequency distributions. We talked about the cumulative frequency distribution. We talked about the relative frequency distributions. All those were just basically distributions. How did we define a frequency distribution? It was just basically a list of values with their frequencies. That's a frequency distribution. I'm sure we can recall what we meant by those things. Frequency distributions was just a list of values with their distributions. That's what we said under descriptive statistics. So now, if I was to list a list of values with their frequencies, then I'm talking about something which can be in this format, a table of such a format, which will have x values and its frequencies. So if it is x values with its frequencies, I'll discover, maybe 0, maybe 1, maybe 2, maybe 3. This 0 has its own frequency, maybe it's a 4. This one has its own frequency, it's a 2. This 2 has its frequency 7. 3 has its frequency 8. So a list of those values of x with their frequencies is referred to as a frequency distributions according to descriptive statistics. So now, if I was to talk about cumulative frequency, I will talk about a list of x values with their cumulative frequency values. The same is happening with relative frequency. If I was talking about relative frequency, I'm talking about a list of x values with the frequencies, with its relative frequencies raw. So that is basically how I'm going to define the probability distribution this time. So what is a probability distribution in this case? Just from the word itself, probability. What are we simply saying? The probability distribution is just basically probability distribution of random variables. We're just simply saying that this lists all the possible values of the random variable. And their corresponding probabilities. So when it comes to probability distribution, what are we simply saying? The probability distribution of a random variable is just basically a list of all the possible values of the random variable and their corresponding probabilities. A list, we're just talking about a list of all the possible values. Remember, we talked about a random variable. A random variable, just talking about the numerical quantities which is assigned to this variable. Any numerical quantity which takes up the possible outcomes of a sample is basically a random variable. So all those possible values assigned, all those possible numerical quantities with their probabilities. So maybe if I have this is a sample space, and then x takes up values to have 0, 1, 2, and 3. So this is a certain experiment, maybe getting heads in 3 experiments. So there's a possibility that I can have 0 heads, I can have 1 head, I can have 2 or 3 heads. So these are the possible outcomes which is assigned to a random variable x. So now there's a possibility now, or maybe I can talk about what is the probability of getting a 0, what is the probability of getting a 1, what is the probability of getting a 2, what is the probability of getting 3 heads. So if I talk about a table or a list of what? These x values with their probabilities, I list in the probabilities of this, then what I have formed in this case is basically a probability distribution. So x can take up values, quantity values. Either what I'm trying to simply say here is that when it comes to random probability distribution can be in 2 cases. Can be of the first case, number 1, where the distribution can be discrete, and there can be a case 2 where the distribution can be continuous. So these are the 2 cases when it comes to the probability distributions. Is the probability discrete or is the probability distribution continuous? So now, when it comes to probability distribution, I'm simply saying that it can be in 2 cases. One, which was simply saying that it can be a situation whereby the probability distribution is a discrete case, or there can be a possibility whereby the probability distribution can be in a continuous case. So what happens if the probability distribution is a discrete case? So in this case, we are simply saying that when it comes to the probability distribution being discrete, probability distribution of a discrete random variable, which is abbreviated as DRV, this time around, when it comes to the probability distribution of a discrete random variable DRV of x, is basically denoted by P of x, or we can simply say Px equal to x. What does that mean? That simply means that we are talking about the probability mass function. So what do I mean by probability distribution being in a discrete case, which is denoted by P of x, or Px equal to small letter x? This is called the probability mass function. So what we're trying to simply say here is that the probability distribution of a discrete case can be expressed in a function form. You can write something as a function. So that function you're writing should be in a form of P of x. So the P of x here is just trying to talk about the assigning of probability to a random variable which is what? Discrete. We're trying to assign probability of a random variable which is somehow discrete. So if the distribution here follows a discrete case, then what I'm going to have in this case will be a function called the probability mass function. That's what we're trying to simply say here. So if it's a discrete case, what I'm going to have will be a probability mass function. So basically, what kind of rules can we have under the probability mass function? We are simply saying that in a situation where, if let's say in a situation we have x1, x2, x3, where up to xc, these are basically c values that our random variable x assumes. So if these are C values that our random variable x assumes, we have to understand that if these are the C values, then there should be a possibility that this x1, which is the first x value which x variable can assume, should be less than x2. The same thing x2 should be less than x3, and the same thing x3 should be less than the next number until I reach xc. Because why am I simply saying so? We're trying to assume that these values are countable numbers, and every time we are counting, obviously this value, the first value I count and compared to the next value is bigger than the previous value. That's why we're simply saying that if x1, x2 up to xc are basically countable numbers which x can assume, then we are simply saying that the probability mass function must satisfy the following conditions. So remember, what is the probability mass function? The probability mass function, it is a probability function which is being formed when it comes to the probability distribution being in a discrete case. So the following condition should be satisfied given that this should be a probability mass function. Then we have the following conditions. What are the conditions? We have the first condition where we are simply saying that the 0 should be less than the probability of getting any xi value. Xi, this is a small letter xi, meaning that the values which the capital letter x, which is a random variable, can assume. So x can assume x1, x2, x3 up to xc. So xi, this I in this case can be 1, 2, 3 up to c. So I can have probability of x1, or I can have the probability of x2, I can have probability of x3, x4 up to xc. So I'm simply saying that every time when it comes to probabilities, the 0 should be less than or equal to the probability of having any of these, and the same probability should be less than or equal to a 1 for all the I, which can be equal to 1, 2, 3, way up to a c in this case. That's the first condition which should be applied when the probability mass function is being considered. The other thing we're supposed to be able to consider is that every time when you look at these values which are the x can assume, we are simply saying that if I look at the summation of I equal to 1 to c of this probability of xi's, the summation of the probabilities of these variables or values should basically be equal to a 1. So the two important conditions here which we are trying to take note of when it comes to the probability mass function is that if x1, x2, x3 and x are values that x assumes, then the probability mass function should follow the following conditions. 0 should be less than the probability of picking only of this, and the same probability should be less than a 1. In short, you cannot have a probability which is greater than 1. So the probability of assigning getting any of those values should be in between 0 and 1. At the same time, what we're trying to simply say here is that when it comes to the summation of all the probabilities, should be basically be equal to a 1. That's what we're trying to say there in this case. Yeah. So now, apart from these conditions, what we're trying to simply say here again is that we are simply saying that we are supposed to be able to note out the following when it comes to the discrete case, to say that this p of x, this is the first point, or the second, yeah. So we're simply saying that this P of X can be expressed by, we can either express this probability mass function by a formula. By a formula, I mean that you can represent it maybe in an equation, or you can present it in a function form. So P of X, this is a function. You can express it in a formula or in a function form. Or you can represent this P of X in form of a table. Remember, this is basically a list of X values with their probabilities. Apart from that, you can express this function in a histogram. I'm sure we still remember how to come up with a histogram. Apart from it being representing in form of a histogram, you are able to represent the probability mass function in form of a graph. So this graph, what kind of graph are we talking about? We can talk about a graph of a stick diagram. So the question can come to say, can you express the following discrete probability mass function as a formula, as a table, a histogram, or you can represent it on as a stick diagram. So, and then the other point you're supposed to be able to take note of as well is that the probability mass function P of X is just basically called PMF because it takes non-zero values only at discrete points of X. That's the other point. So with these rules which we've just stated right now, we are able to solve a number of questions when it comes to discrete cases. So we've understood when a probability distribution can be in the form of a discrete case, and some of the rules we are able to follow when it comes to discrete random variable distribution. Okay, I want us to look at a certain practical example concerning the DRV, which is the discrete random variable case of the probability distribution. So what do we have here? We are being told that if a university has received a consignment of 5 identical personal computers from the manufacturer, and then from the information we have is that 2 of the 5 are defective, and then if a sample of 2 pieces is randomly selected, the following is the sample space for this experiment. I'm sure you can remember, recall this question. We've done this question when it came to, is it counting techniques? I think so. On the assigning a sample space, assigning the sample space, something like that. So if you're able to check through your previous lessons and the previous notes, you'll be able to find this question. We did it when it comes to assigning and finding the probability and so forth. Yeah. So if the sample of 2 pieces is randomly selected, the following is the sample space for this experiment. So we have the following sample space there. So in the sample space, we have a total number of, the elementary event, we have D1, D2. D1, D2 means that this is a possibility when, assuming that the 2 computers which were selected, the first one was D1 and the second one was D2. D1, N1 means that the first one which was selected was D1 and the second one which was selected was N1. So we have to understand, first thing you're supposed to understand is that there are 2 kinds of cases, or 2 kinds of computers here. There are those which are defective and there are those which are non-defective. So the question is, if X is the number of non-defective pieces if X is the number of non-defective pieces, so mean that from the sample space here, D represents defective and N represents non-defective. That's an understanding you're supposed to be able to have. So since we have two defective computers, no wonder we have only two labels there, D1 and D2, which represents two defective computers. And N1 to N3 represent the non-defective computers. So there's a possibility that the two computers which were selected, there can be a possibility that both of them can be defective. There can be a possibility that maybe one of them is defective, or there can be a possibility that none of them is defective, and so forth. That's the assumption you're supposed to be able to have under probability here. So now under the question now here says that if X is the number of non-defective pieces in the selection, determine the probability distribution and the cumulative distribution function of X. So that's what we're trying to find, and that's what we're trying to locate in this question. So we'll start. What is the probability distribution? The probability distribution is basically a list of probabilities for the random variables. So we have to find the probabilities of this distribution later on and so forth. First thing is first, let's look at the random variable X. Before we look at anything, we're looking at the random variable X. So we have to understand that this X is taking up the number of non-defective computers in the selection. So you can simply say that X is equal to the number of non-defective computers. So if you're talking about the number of non-defective computers in the selection, what kind of values will X obtain? Therefore, we can simply conclude that X can take up situations or numbers where you can simply say X can equal to 0. X can be equal to 0 if in the selection of those two computers we didn't have any computer which was non-defective. For example, maybe picking D1 and D2. In picking this, there's a possibility that I did not pick any non-defective computers. All the computers I picked were defective. So this X, random variable X, can take up what? 0. This random variable X can take up what? 1. If it is taking up 1, it's an assumption that among the two computers which were picked, one of them was non-defective, whilst the other was defective. And it is a possibility that X can take up 2. 2 means that both computers which were picked were what? Non-defective. For example, in a situation where we picked N1, N2, N1, N3, N2, N1, those are non-defective computers. Now, we have to understand that there is no way X can take up 3. No. Why? Because how many computers did we pick? We only picked 2 computers. So there's a possibility that X can be equal to 0, X can be equal to 1, or X can be equal to 2 and not 3. Because the experiment only looks at picking 2 computers. We pick the first computer and we pick the second computer. So the random variable X will take up values from 0 way up to a 2. Now, what are we simply saying representing this? We are simply saying that we can have when we are simply saying X can take up 0, 1, and 2, in a situation where we can simply say that this X can be equal to 0, 1, or 2. It can be X can be equal to 0 if we are trying to consider, or maybe when we have a situation where we picked D1, D2, or when we picked D2, D1. That's the understanding you're supposed to be able to have there. X can be equal to 1 in a situation whereby the only non-defective computer we have is only one non-defective computer. So in a situation from the sample space, the situations or the elementary events which has only one non-defective, it is this guy, that guy, that guy, that guy, that guy. So all the cases where we have only one non-defective computer, it's a situation which is giving us when x can be equal to 1. So x can be equal to 1 when we have a situation whereby we have d1 n1, when we have d1 n2, when we have d1 n3, when we have d2 n1, when we have d2 n2, am I correct? Yeah. When we have d2 n3, when we have n1 d1, when we have n1 d2, when we have n1 n2 d1, when we have n2 d2, when we have n3 d1, when we have n3 d2. So these are simply explaining the process of us assigning 1 to x, given that we just picked one non-defective computer. What about if both of them were non-defective? We're looking at all the situations when we had both to be non-defective, and the both being non-defective, this is when x is equals to 2. This is when, in a situation when we have n1 n2, in a situation when we have n1 n3, in a situation when we have n2 n1, in a situation when we have n2 n3, and in a situation when we have n3 n1 and n3 n2. That is in a situation when we have x being equal to 2. And it is through this information that we are going to have, or we are going to create, the PMX. What is the PMX? The probability distribution, or the probability mass function for this discrete case. It is through that situation we're going to have the probability mass function. So from the probability mass function, what we know is that the probability mass function is basically just a list of x values with their probabilities. So a list of x values with their probabilities. That's what we're trying to say there. So we want to create the PMX, and then later on we can create the cumulative mass function. So now, the probability distribution, first I'm going to come up with the probabilities. X takes up 0, 1, and 2. So I'm going to find the probability of 0. I need to find the probability of 1. I need to find the probability of 2. After finding those probabilities, so that I can later on put them in a what? In a table, then I will be able to have the probability distribution of this case. So what am I going to have? What is the probability of 0? The probability of 0, it is in a case whereby how many elementary events do I have when x is equals to 0? When x is equals to 0, you only have 2 elementary events, d1, d2, and d2, d1. Out of the total outcome, the total outcome in this case from the sample space was 20. So basically, probability of 0 is giving me a 2 over 20, which is just basically equal to what? 1 over 10, which is the same as saying 0.1. That's the probability of 0. What is the probability of 1? The probability of 1, we're talking about in a situation whereby we only had one non-defective computer. So all these elementary events, when we count them out of the total number, which is a 20, will give us a probability of x equal to a 1. So x equal to 0, x equal to 1, we're going to have the elementary events which has x equal to 1 is basically 12 out of the total number 20. So 12 over the 20, which will be basically the same as 6 over 10 when reduced to those terms, which is just basically the same as 0.6. The same is happening when probability is equal to 2. Probability equal to 2, x equal to 2. counting these, we have 1, 2, 3, 4, 5, 6. So we're going to have 6 over the total outcome, which is a 20, which is going to give me 3 over 10, which is equals to 0.3. So that is the assumption. Those are the probabilities. So that when we are able now to form what is the probability distribution. So the probability distribution in this case becomes, what is the probability distribution? We remember define the probability distribution to be just basically a list of the x random variables with their probabilities. So I'm going to have a table. Remember, we can represent a PMF in a table like this one. This can be the x values. X values are running from 0, 1, and the 2. And this column will be the probabilities of x equal to x. The probabilities. So what is the probability of this 0? The probability of this 0 is basically 0.1. The probability of this one is basically 0.6. And the probability of this is basically 0.3. And then, with that being done, I've found the probability distribution. But there is another part which the question said to say, can you form the cumulative probability distribution? What is the cumulative? Cumulative, just as we did in descriptive statistics, the cumulative probability distribution is basically just a summation of all the successive probabilities. The summation of all the successive probabilities. So the cumulative probability distribution denoted by the capital letter F of x. This is just basically the probability of x less than x. So what does this mean? This just means summing up the successive probabilities. So I can form another column which will be the capital letter F of x. So the capital letter F of x will be just summing up with this. So in the first row I'm going to have 0.1. The second row will be 0.1 plus 0.6, which is going to give me 0.7. 0.7 plus 0.3, which is basically going to give me a 1. So from that table there, I've answered two things at once. I've basically formed the probability distribution. I've at the same time formed the cumulative probability distribution. So now, look at what is happening here. Based on those rules we said, the summation of all the probabilities here should be basically equal to 1. So to prove that this is indeed a valid PMX, we are simply saying 0.1 plus 0.6 plus 0.3. The summation in this case should be equal to a 1. And to know that you've done the right thing, the cumulative probability distribution here, as you are summing up, the final answer supposed to have here should be a 1. Then you're on the right track. We are okay? And then the other part I'm going to talk about, it is, let's say there is a part or a question which says that after finding a probability distribution, the question continues to say, can you portray the probability distribution of x by a graph and a probability histogram? In other terms, we're simply saying this question says that show the PMF on a graph and a histogram. So I want to show the probability distribution not only in a table. Now this time I want to show it on a graph. At the same time I want to show it on a histogram. So the graph which shows the PMF is basically called the stick diagram. So the stick diagram will be something which will be written in this format. We have the x-axis and the y-axis in this case. So the x-axis will have the random variable x, and the y-axis will have the probability of x equal to x. So what do I have here? I have 0, I have 1, I have 2. And then from the probabilities, I have 0.1, 0.3, and 0.6. So the stick diagram, I'm just going to be able to draw sticks. From 0, I will draw a stick reaching to 0.1. From 1, I will draw a stick reaching to 0.3. From 2, I will draw a stick reaching to this is 1, 0.6, and it is 2, 0.3. So this is how my stick graph or my stick diagram will be. How will be my histogram look like? I'm sure you can recall how the histogram look like. Basically the graph are attached to each other, there is no space in between. So I'm going to have the graph for 0, I'm going to have the bar for 1, and I'm going to have the bar for a 2. So this will be my 0, this will be my 1, and this will be my 2. This is 0.1, this is 0.3, and this is 0.6. Same, having the probability of x inside and the random variable x. So this is my histogram and this is my stick diagram. So with what we've done so far here, we've just basically answered the question which involves the discrete random variable case, where we are simply saying that probability distribution which follows the discrete random variable case, it is a situation which we call it to be the probability mass function. From it, we are able to even find the cumulative probability distribution, which is basically just a summation of all the successive probabilities. Thank you very much. And next, we are looking at the the continuous case, which is the probability distribution involving a continuous case.